Welcome back. We are going to start Chapter 4, Section 1, Introduction to Systems of Differential Equations. So, let's get started. Alright, so what's a system of equations? Well, we can get one system of differential equations by having this coupled spring system. You got mass 1 and mass 2. They're attached by springs, and you have this distance x. You're trying to predict where the mass 1 is by using position x, and mass 2 is by using position y. Alright, so what we need to do is decide what's going to be positive. So anything with an arrow pointing in this direction is going to be positive. So to do that, we need to look at the net force acting on each mass right here. We've got our pictures. So mass 1 looks like this. We've got a negative force pointing in this direction right here, and that's this term right here. And we've got a positive force pointing in this direction, and that's this term here. Alright, so that's our first equation. And then our second equation is the forces acting on this mass. You've got this force right here acting on mass 2, and that's this one right here. And then you've got this force right here acting on mass 1. And so that gives us 2. As you see here, the first equation has a y here, but the derivative is with x. But here you see there's a derivative of y, and actually a second derivative of y, and then you have an x over here. So these are two second-ordered coupled differential equation. Whatever happens to x here also affects the y. Whatever happens to y here also affects the x. And so this is a system of differential equations. And we can solve this using the information that we have, and we'll talk about a solution method here as we go on. So another example for a system of differential equations is the circuit problem right here with two loops. So what you have to do is, the first thing we're going to have to do is we have I1 flowing this way and I2 flowing this way. So I here, the current going down, is I1 minus I2. So we need to keep that into effect because our first thing, so we're going to go around this loop. I'm going to start here and go this way. So if I do that, I get this term right here. And then we're going to come down this way. And now, since my loop is going the direction of my current, it's a negative value. So I get that there. I get the resistance times the current in there. And then we're going to come over this way and then back up. Well, I'm going from the minus to the plus. I'm going from a lower potential to a higher potential. So that's a positive. And all those added up should equal 0. Now we're going to do the second loop. So I'm going to start here with the capacitor. And so I'm going with the current, so that the voltage decrease and the voltage drop across the capacitor is 1 over C times the charge on the capacitor. And then I'm going to go this way. And then I'm going with the current, so the voltage drop there is a minus R2 I2. And then I'm going to come down this way and then go up this way. Now I'm going opposite of the current because I'm going in this direction. So that's going to be a positive value, and that's going to be R2 times I1 minus I2. And now we have a system of equations, and we can plug the numbers in for the values that we have. But as we see here, we have a Q here, and we have I1s and I2s also in each equation. So what we have to do is have less. I have two equations, so I can only have two unknowns. So I have to represent Q some other way. So what I'm going to do is I'm going to take the derivative. I'm going to take the derivative here with respect to time of this whole equation. And if I do that, I get the derivative of the charge with respect to time. And if you remember, that's the current in the branch where the capacitor is, and that current is I2. So I get this expression. Then I take the derivative of the next term, I get that, and the derivative of that, and they all have to add up to be 0. So if we go around and we plug in the numbers, I take this one and I plug in the actual value for the inductance L and the resistor R1, I get this equation, and then I plug in the values for the C and the R1 and the R2, and I get this equation. So now I have a system of equations, and they're coupled because I have I1s and I2s in both, and then we can solve these, and we'll talk about some more. So it's our second. Our third system is a mixing problem. So I'm going to review what we need to do with mixing. So the whole idea is we're trying to figure out the change in the pounds of salt in the system. And so we have X pounds in this vat and Y pounds in this vat. And to get the change in the pounds of the system, I have to know how much is coming in and how much is going out. So to do that, that basically is going to convert to the rate in times the concentration in minus the rate out times the concentration out. Well, what's a rate? Or I should say, what's the concentration? It's the amount of salt in the system divided by the total volume of the vat. And then the rate is the amount of volume per second that's coming out. Okay, so if we look at the first vat here, if we look at tank 1, we want to find the change in the X amount of salt per unit time. So I have fresh water coming in at 20 gallons per second, and it has fresh water. It's 0 concentrations of salt. And then I also have coming in 10 gallons per minute of water from tank 2, and it has a concentration of the amount of pounds in tank 2 divided by 200 gallons, the amount that tank holds. And then I have some going out of tank 1, and so I have a minus 30 gallons per minute coming out with a concentration of X divided by 100 gallons, and that's what's in tank 1. So that's equation 1. That first term will go away, and we can move the other ones over. My minus sign kind of disappeared here. I apologize for that, but I'm going to keep moving on. So now I got to do my Y, my change in the pounds of salt in tank 2. So this is tank 2 equation right here. So I need to know what's going in or what's going out. Let's start with what's going out. So I have this term going out of tank 2 at 10 gallons per minute and at this concentration. I have this amount going into tank 2, so that's positive. 30 gallons per minute going in times X amount of salt divided by 100. And then I also have this term here, 20 gallons per minute going out here with the same concentration. So you could add these two together, but these are my two equations and two unknowns for the system. And so we can solve this for what an equation for the pounds of salt in one tank and the pounds of salt in another tank. Alright, so how do we solve these systems of equations? Well, there's two ways to solve them, I should say. What I'm going to show you here is, let's say we have a higher order differential equation, and we can't solve it with the methods we've talked in class so far. What I'm going to do is show you a substitution method so you can solve the system with the equations we have in class. Now, this equation we could solve already, so I'm just using this as an example. So what we're going to do is we're going to create a system of first order differential equations. So what I'm going to say is the first derivative of x is equal to a new function I'm calling h. Alright, so if I take the derivative, if I take my second derivative of x, I'm going to claim that's equal to a new function called g. And knowing that a second derivative of x is equal to g, then I can take my derivative of my h function, and that should also be equal to g. And then I'm going to do that again. Well, if I take the third derivative of x, that should be equal to g prime, right? So now I can take these substitutions and plug it back in to my original equation up here, and I get this equation. So I have this first order equation, that's equation 1. I have this first order equation, that's equation 2. And then I have this. I have 3 first order equations here, right here. And that also describes the same system right here. So these are equivalent. Okay. And you're asking me, well, with the methods we've talked about in class, I could solve this anyway, so why am I doing these substitutions? Well, I wanted to show you the substitution method first. So what I'm going to show you now is an equation, a problem that we can't solve because these coefficients here are not constant. So we don't have a way of solving that yet. And so the way we're going to solve that is we're going to use the substitution method. So I'm going to say for the first one is x is now equal to h, some function h. And now if I take my derivative of x, I'm going to claim it's equal to g. And if I do that, then h prime is equal to g. And then I'm going to say my second derivative of x is equal to g prime. And if I make those substitutions back into my equation, I get this equation, right? I should say this is my equation that I get from making the substitutions from all of these ideas. And what I now have is a system of first-order differential equations that I should be able to solve. Actually, I only think I need these two. This one shouldn't matter. What I have is a system of 2 equations now. You see here I have a system of 3 equations because I had my n was 3, so I need 3 equations. Here my n is just 2, so I only need 2 equations. Now I can solve these first order equations. Doesn't matter if I have a coefficient of t in there. I have mechanisms to handle that in our solution methods with first order equations. So we should be able to solve this system of equations now, but if we left it in this form up here, we can't solve it. Alright, so how do we solve these systems of equations? Let's look at another example. Let's look at problem 18, where the derivative of x with respect to time is equal to y, and the derivative of y with respect to time is equal to x. So here's the deal we're going to do. We're going to do a substitution method here also. What I'm going to do is I'm going to take a second derivative. I'm going to take the derivative of this whole expression. So the second derivative of y has to equal the derivative of x. Well, I know what the derivative of x is. It is right over here. And that's telling me the derivative of x is equal to y. So if I plug that in here, now I've got an equation with just y's in it. Or I've got an equation I know how to solve. So we can solve this. We can find the characteristic equation, and then find the roots of that equation. And then we're going to plug it back in. So that's the definition of y. Now I've got to find my x. Well, that's pretty straightforward. I can either use this expression or this expression to figure out x. So I'm going to use that the derivative of y is equal to x. So I'm going to use this idea right down here. So all I have to do is take the derivative of my y, and I should get x. Now if I do that, I get this expression. So now I have an x, and now I have a y. So I've solved my system of equations. And we're going to need initial conditions here too to find out what C1 and C2 are, at least two. For every independent variable, you need at least one. You have to have one initial condition. Alright, so let's look at problem 21 on page 236. So it says that the first derivative of x with respect to time is equal to 1/2 y, and the first derivative of y with respect to time is equal to a minus 8x. So what I'm going to do is take the derivative of take the second derivative of y, which should be equal to the minus 8, the first derivative of x, but I know what the first derivative of x is. The first derivative of x is this. So if I make that substitution in, sorry about that, I make that substitution in, I get this expression, and if I set equal to 0, I get a second order linear differential equation with constant coefficients. Find the characteristic equation, solve for the roots. So our solution for y needs to be this. Now, how do I find x? Well, I know that the derivative of y is equal to minus 8 x of t, so there's my derivative of y, and now I can just divide by a negative 8, and so I get this expression for x, and now I have solved my system of differential equations. Alright, let's try one example here. Let's look at problem 25 on page 236. So this says the first derivative of x with respect to time is equal to minus y, and the second derivative, the first derivative of y with respect to time is equal to 13x plus 4y. So what I'm going to do now, and we have some initial conditions now. So what I'm going to do is take the second derivative of x with respect to time, which is equal to minus y of t, a minus the first derivative of y of t, and I know what that is equal to. That's equal to this right here. So if I plug that back in there, and then I also know that y, a negative y, is equal to the first derivative of x, I can plug that in for the y term right here, which is this is the same term here. And I get this second order differential equation. Let's group it back together a little cleaner, and now you've got this. We are familiar with solving these. I get this characteristic equation, which solve for its roots. That's the roots. So x has this solution to it. Well, what is y? Well, then according to this, y of t should be equal to the negative first derivative of x with respect to time. So there is your solution for y. Now I have to find my initial conditions. So at t equals 0, x equals 0. So that's basically the sign of 0 is 0. So that gets rid of this. So this whole expression is equal to 0. And we're left in cosine of 0 is equal to 1. So this is basically going to tell us that C2 equals 0. Now that I know that C2 equals 0, I can plug in my y equation. I've made the C2 0, so the square roots of 17 disappear. And I get this expression. So again, sine of 0 is 0, so this whole expression will equal 0. And the cosine of 0 is 1, so this tells me that C1 has to equal 3/2. So let's plug that back into x. So this is my x equation. Plug it back into y. This is my y equation, and this solves that system of equations. I hope you've learned or have a better understanding of how to solve some second-order differential equations. We'll do some. We will do some more in class. So I'll see you in class.